flux measurement and torque estimation. So we're seeing an industry trend, and I think people have been doing this for a while, to really calculate the flux and really evaluate what your torque estimation is. And people are starting to think use flux a lot more. So torque cannot be measured directly in a vehicle, not practically. But flux can be used to estimate torque. And you know, we've got our equation here, and I'm sure somebody will hop up and tell me I wrote it wrong. And you might say, what is flux? Well, it's magnetic strength or the flux linkage is the magnetic field going through an area. So it's how strong is my magnet. So flux cannot be measured directly, not in a motor, not really effectively. And flux is loss and temperature dependent. So it makes it quite difficult to do in a vehicle without a lot of thermocouples, without a lot of knowledge of the states of the system. My other fun fact about flux is that everyone seems to have their own method of calculating flux and estimating flux, you know, using different manipulations of the equations. And many times we're seeing lookup tables used. So flux is difficult to calculate accurately. And this is where I think HBK has done some cool things to help. So we look at the technical implementation. You know, you can go through some equations and you can kind of look at some math and figure out, you know, what your flux is. And from a measurement standpoint, we measure voltage and current, V and I. We can look at temperature to estimate resistance. Or in a measurement test stand, we can use mechanical power to assume rotor loss and assume loss and kind of manipulate this equation. There's some clever stuff. We can discuss that. And then we have the speed of the unit. We can rearrange these equations to get our flux. So basic example is, you know, lambda equals V minus losses over speed. And what we end up doing is doing, you know, DQ0 calculations for voltage, DQ0 for current, which I have displayed here. Our software can calculate that in the real time and display that as a scope trace. So flux can be calculated in many ways. So we look at a motor flux example. I just implemented that simple equation. I know you're probably not using that. But we measure the three-phase voltage, we estimate the resistance, we execute the DQ0, and we calculate flux. And we can see our equations here. These are all implemented in the hardware in the real time, available for feedback to our hardware in the loop. And then we have our example. So we have torque. Torque is constant, and we're sweeping speed. We have our voltages in blue, our currents in red, our IQ in other red and maroon. We have our VD, VQ in blue and other blue. And then we have our flux D and our flux Q in green and purple. And in the real time, we can view that as a scope trace. And you can see the flux as we're ramping up and really understand those changes as they're happening. So we can start to understand our control and start to make things like flux maps very easily. We don't have to take a scope, make a measurement, go to MATLAB, process, then understand. You can have your efficiency and your flux in the same place. So we offer custom calculations. You can enter your own proprietary flux calculation. It's going to be time aligned to torque because we're measuring that on the same timestamp. And then if you want to use temperatures, we can also bring in your resistance, your temperature for doing that loss estimation. So we give you a lot of flexibility. But with high accuracy sensors, with high accuracy amplifiers, you can get a very high accuracy measurement of your flux. And we do have some cool methods for calculating flux on our own that we can implement if you want like something to compare to. Now, the other thing we're seeing is the controller's calculating torque on its own. You know, it's calculating flux, it's getting to torque eventually. So we can compare measured values to the controller estimation by measuring the CAN bus of the system. And now you're getting your voltages, your currents, your torques, your fluxes, and your calculated torque, your calculated ID, your calculated IQ from the inverter. Play that in all place. So we can measure the CAN on the same timestamp, compare that to your values. You can look at what that difference is and start to calibrate your torque estimation. And here's an example. We have torque command in black, real torque in pink, and the torque command doesn't actually get to the controller until this point. And then we get this nice, you know, kind of estimation. This is an experimental controller, so it's way off. And we can also do that for our RMS values. We can do that for any value in the controller and in the high accuracy calculation. So calibrate your controller and lookup tables with time-aligned CAN. And the calculations happening in the real time. All right, measuring harmonics, one of my